In this segment, we'll finish up our proof of the theorem of the maximum and spend a little bit of time thinking about the economic implications of this important result. So we'll start by reminding ourselves of what the theorem states, then quickly review a couple of concepts having to do with real sequences, then we'll finish up the proof of the theorem and then discuss its implications. So here's a reminder of what the theorem of the maximum states. So we have two metric spaces, capital theta and x. Theta is interpreted as a set of parameters and x as a set of decisions or actions. Gamma is a correspondence called the constraint correspondence, and that tells us for any given theta what set of actions is feasible, and we assume that this is compact valued. F is the objective function that the decision maker is trying to maximize, and this is real valued and continuous, and the payoff to the decision maker depends both on the action taken and on the value of the parameter. And we define f star of theta as the maximized value of the objective function. So this is the highest payoff that can be attained by the decision maker if the parameter is theta and the action chosen is feasible at this parameter value. We define gamma star of theta as the solution correspondence. This consists of the set of actions that yield the highest payoff when the parameter value is theta. And the theorem states that if gamma, the constraint correspondence, is continuous at theta, then f star, which is the maximized value of the objective function, is also continuous at theta, and the solution correspondence gamma star is compact valued and upper hemicontinuous at theta. And keep in mind that the result does not guarantee lower hemicontinuity of gamma star, and we want to think about the implications of this later. Now we've proved that gamma star is compact valued and upper hemicontinuous in the last segment, so to finish up we just need to prove that f star is continuous at theta. Now before we do this, let's remind ourselves of a couple of concepts having to do with real sequences. So if xn is a real sequence and x is a real number, we say that the limit superior or the lim sup of xn is x if two conditions are satisfied. First, for any epsilon positive, there exists some number m such that once you get past this term in the sequence, every subsequent term is less than x plus epsilon. And this must be true for any epsilon positive. And second, for any epsilon positive in any natural number k, there exists a larger number L such that xl is larger than x minus epsilon. And this must be true for any epsilon positive. Another way to think about this is that if the lim sup of xn is x, then for any epsilon positive, there are just a finite number of terms larger than x plus epsilon. That's the first condition. And secondly, there are an infinite number of terms that lie within an epsilon neighborhood of x. And these two conditions guarantee that the lim sup of xn is unique. Now it may be the case that there is no finite number x for which these two conditions hold. For example, if xn contains a subsequence, xnk, that goes to infinity, then the first condition can't hold, and we write the lim sup of xn to be infinity. And if xn itself goes to minus infinity, then the second condition can't hold, and we write lim sup of xn to be minus infinity. And we can define the limit inferior or lim inf of xn in exactly the same way by suitably adjusting these conditions. So for example, for the first condition we would require that for any epsilon positive, there exists some number m such that xn is larger than x minus epsilon for all n greater than equal to m, and so on. Now it can be shown, and you should verify this, that the sequence xn converges to the point x if and only if both the lim sup and the lim inf of the sequence are equal to x. And furthermore, it's true that every real sequence xn has a subsequence xnk that converges to the lim sup, and the same holds for the limit inferior. Every sequence has a subsequence that converges to the lim inf of that sequence. Now we can finish up the proof of the theorem. Recall that we've already shown that the solution correspondence is compact valued and upper hemicontinuous at theta, so all that remains to be shown is that f star, the maximized value of the objective function, is continuous at theta. So consider any sequence of parameters, theta n, that converges to theta. We need to show that the sequence of images under f star converges to the image of theta. This is true if and only if the function f star is continuous at theta. Now let's use one of the facts that we've just discussed. Regardless of whether the real sequence f star of theta n converges to f star of theta, there exists a subsequence which we'll call f star of theta nk that converges to the lim sup of f star of theta n. Now let theta nk denote the sequence of parameter values that are associated with this subsequence f star of theta nk. And note that this must converge to theta because it's a subsequence of theta n and theta n converges to theta. Now we're going to construct a sequence of optimal actions, let's call it xnk, that corresponds to this sequence of parameters theta nk. So xnk is an element of the image of theta nk under the solution correspondence gamma star. So we have a sequence of parameters, theta nk, a corresponding sequence of optimal payoffs, f star of theta nk, and a corresponding sequence of optimal actions, xnk. Now note that f star of theta nk, which is the optimized value of the objective function when the parameter is theta nk, must be equal to f of xnk theta nk. This simply follows from the fact that xnk is optimal when the parameter is theta nk. So it must yield the highest possible payoff, which is f star of theta nk. Now we'll use the fact that gamma star, the solution correspondence, is compact valued and upper hemicontinuous at theta. Now since it's compact valued, we can use the sequential definition of upper hemicontinuity. And this means that there exists a subsequence of xnk, let's call it xnl, such that xnl converges to a point x, which is in the image of theta under the solution correspondence gamma star. This is just applying the sequential definition of upper hemicontinuity, given that gamma star is compact valued. Now to get xnl, we've extracted a sequence of optimal actions, and we'll let theta nl denote the corresponding sequence of parameters. In other words, xnl is an optimal action when the parameter value happens to be theta nl. Note that the theta nl sequence must also converge to theta, because it's a subsequence of theta n, which converges to theta. Now we'll use the continuity of f to finish up the proof. Now since xnl converges to x and theta nl converges to theta, the sequence of ordered pairs xnl theta nl converges to the ordered pair x theta. And since f is a continuous function, the sequence of images f of xnl theta nl must converge to the image of x theta under f. Now since x is an optimal action when the parameter is theta, f of x theta is equal to f star of theta. And furthermore, since xnl is optimal when the parameter is theta nl, the image f of xnl theta nl is equal to f star of theta nl. It's the highest payoff you can attain when the parameter is theta nl. So what we've shown is that the sequence of images f star of theta nl converges to f star of theta. Now recall that the sequence of images f star of theta nl must converge to the lim sup of f star of theta n. That's because the sequence f star of theta nl is just a subsequence of f star of theta nk, and we know that the sequence f star of theta nk converges to the lim sup of f star of theta n. So what we've done is to show that the real sequence f star of theta nl converges to f star of theta, and we've also shown that f star of theta nl converges to the lim sup of f star of theta n. Put these two facts together and we see that f star of theta is equal to the lim sup of f star of theta n. Now notice that throughout this argument, we can easily replace lim sup with lim inf. That's because every real sequence has a subsequence that converges to its limit inferior. Now if you run through this argument using lim inf instead of lim sup, you'll get different sequences of parameters. So theta nk will be a different sequence of parameters, and xnk will be a different sequence of actions, and so on. But you'll reach the same conclusion. You'll find that f star of theta is equal to lim inf of f star of theta n. And since the lim sup and the lim inf of this real sequence are both equal to f star of theta, the sequence itself must converge to f star of theta. And this is exactly what we needed to prove in order to show that f star is continuous at theta. So we finished our proof of the theorem of the maximum. In the last segment we showed that gamma star was compact valued and upper hemicontinuous at theta, and we've just shown that f star is continuous at theta. Now let's think for a minute about the economic interpretation of this important result. Now here's a simple example where the set of parameters theta is a subset of the real numbers, and so is the set of actions. And the constraint correspondence shown here in gray tells us what's feasible at any given value of theta. Now notice that the constraint correspondence is compact valued and upper hemicontinuous at theta 1. So the theorem of the maximum tells us that the solution correspondence, which is shown here in red, must also be compact valued and upper hemicontinuous. Now in fact it is compact valued as shown, but it's not upper hemicontinuous at theta 1. You should check that the solution correspondence shown here violates both upper hemicontinuity and lower hemicontinuity at theta 1. So this kind of solution correspondence is ruled out by the theorem of the maximum. However, if we make a small change and allow the image of theta 1 under the solution correspondence to have two elements instead of one, as shown here, then this solution correspondence is admissible under the theorem of the maximum. You can verify that at theta 1, the solution correspondence satisfies upper hemicontinuity, even though it fails to satisfy lower hemicontinuity. Now what does this mean economically? Well, first of all, the theorem of the maximum tells you that it's entirely possible that the action you choose is far away from the optimal action. So if the true parameter is slightly above theta 1 and you believe it's slightly below, you may choose an action that is far from optimal. However, the theorem also tells us that this won't have major payoff implications because f star is continuous in theta. Getting the parameters slightly wrong can give you an action that is far from optimal, but it won't give you a payoff that is far from optimal. The other thing you should make note of is whenever the solution correspondence fails to satisfy lower hemi-continuity, so there's a jump in the solution correspondence, at that point there has to be more than one optimal action. In other words, the solution correspondence can't be single-valued at a point at which it fails to satisfy lower hemi-continuity. So there's a link between the continuity of the solution correspondence and the multiplicity of solutions. And I'll stop there for this segment.